report on this computer. So we will, hold on a second. Okay. Okay, so basically, I think you guys really got the gist of this from what I remember, because I looked at your results. They were really good. Okay, but we'll go through it. And please take your time. If there's anything, do not feel embarrassed that you have to jump in. Like sometimes I see your hand raised on the screen, sometimes I don't. So feel free to just, you know, butt in as I'm talking. Trust me, I will not be upset. Feel free to say, can you hold on, because I'm checking my answer, or I don't get the same answer and I can't see where I made a mistake. We'll try to figure it out. Fair enough. So don't be, okay. Now, this was the problem at hand. We had a beam that had, of course, let me just, I like annotating at the same time, okay. So we had a beam that had a uniformly distributed load and a concentrated load, okay. And basically this, of course, if you remember, this is how we designate steel beams. The W stands for a wide flange section, and people used to call that a H section, but they call now a wide flange section, okay? We do have other ones called HPs. I won't get into that. And of course, this represents the nominal depth of your member, okay? So in other words, this thing measures approximately 310 millimeters. And this is what the mass per unit length is in metric. In other words, this is 21 kilograms per meter, okay? If you happen to have a problem in imperial, you end up getting a W12, let's say a W12 by 19. Remember, this is 12 inches. 19 is already in pounds per foot. Therefore, you don't have to convert that into a force, but you do have to worry about that if you're working in kips. Okay, this is in pounds, and of course, if you're looking kip inch, this is kip pound per foot. So you have to worry about the units if you're doing something in imperial. Just to remind you, I think we did an example of an imperial one in the lecture. Okay, so basically, what you want to do is you want to calculate the deflection, and by the position or the superposition, what we'll do is we'll calculate the deflection caused by the uniform distributed load, then by the concentrated load, and of course, but if we do the calculations where we want to calculate the deflection, we can do the algebraic sum of each one, and that's what we're going to be doing right now. So we start with the distributed load, okay? So calculate the self-weight of the beam. So basically here you're going to have to convert the 21 kilograms per meter into some kind of kilonewton. In other words, you have to convert the mass into a force. And the way we do that did they cover this in physics properly, that you just multiply by the force of gravity, or the acceleration of gravity, and that converts it into a force? And of course, because if you remember, 1 Newton is equal to 1 kilogram accelerating at a speed of 1 meter per second squared, and that's what a Newton is. I don't know if they cover this in physics. They should explain to you how, you know, like what happens to a mass and when you want to convert it into a force, and I hope they did that. So basically, so here I have 0.2 kilonewtons per meter because my distributed load is in kilonewtons per meter, and therefore I will add it to the 15. I'll end up with 15.2. Now I got that, of course, what I need to do is determine the deflection right at the center here. I've got a span of 5 meters or 5,000 millimeters. And the best thing to do here is I look at my diagram. I see how my diagram, when you're looking at these diagrams, what you have to look at, and if you want to use the beam formulas, okay, you have to look at your supports and you have to look at the loading, okay? If you have the same supports and you have the same loading, then you can use the beam diagrams, all the formulas that correspond to that diagram you see in the beam formulas, okay? So that's what you have to worry about. Now, in this case here, I don't know if this is going to take a while. Okay, so I'm going to go back. So basically, I must have used this. That's why it's okay. So here we go. Okay, so they always start with the most common situation that we're going to have in everyday life. In other words, you're going to have a beam that is simply supported. Okay, So this is simply supported beam, and that's what we have. Okay, in other words, it doesn't matter whether the pin is there and the roller is there or vice versa. It's a simply supported beam and a uniformly distributed load right across the whole span, and that's what you have here. And therefore, since our problem corresponds to this diagram, we can use the anything here to calculate any of these values that we want to know. In other words, we want to calculate reactions and shears. Well, this is the formula that we'd use to calculate the value here for the shear, the reaction here. We want to calculate the moment at the center, this maximum moment here, then I would use this equation here, okay? And that will give me the maximum moment there. And because you want to know the maximum moments when you're designing something, this becomes very practical. If you want to know the moment anywhere along the beam for some reason, then this would be the formula that you use. If I want to know the moment right here or right there, this is what I do. And of course, X means that you're starting from the left-hand point, and where if I want to know the moment there. And of course, if I want to know the maximum deflection at the center, this is the equation that I'm using. And of course, this is what we've been using for our problem right now, because that's what exactly we want to do. And then we can calculate the deflection at any point along the beam based on this formula. So that's what's nice about these little formulas. They give you information that you might need either in your analysis or to, for whatever you want to do with regards to designing a member. So in our case now, so we're going to be using this formula here, 5WL to the fourth over 384 EI. And, oops, sorry, here we go. So here's our equation, okay? Now I put IX, guys, because in steel, okay, in steel, this is the steel, okay? And basically when you're placing this beam here, it would be placed like this, the support would be here, okay? And this here is what they call the X-axis, okay? And therefore this is the stronger axis. In other words, where you have, this is called a flange, that's called a flange, that's called a web. So that's the strong axis. So whenever you're placing a beam, you're gonna be placing it with, because then you also have this axis here, this is called the weak axis, this is YY. And of course, the moment of inertia with respect to YY, it's much less than with the respect to XX. So that's what we call it, XX or XY. And of course, the value of steel, okay, is 200,000 MPa. Now, if during the exam, just remember, in imperial, the assumed value of the modular elasticity is 200,000 MPa, and of course, in imperial, is 29,000 KSI or 29 million PSI, whatever you want to use. So here we go. The only thing you have to be careful about here are your units, okay? So remember, the best thing to do is put the span in meters, millimeters. So therefore, this cancels that, that cancels that, that cancels that. That's under the, and it goes up here back to the numerator and becomes millimeters. And therefore, I have the right units. And if you do the math correctly, okay. And guys, like I said, when you're doing something in metric, okay, 1 decimal place, ample, okay? In other words, 16.7 or 17 millimeters, it's exactly the same value. I don't think that you have to worry about 0.3 millimeters in your calculations, okay? Nobody's going to actually see that. So anything to 1 decimal place, and if you're doing it in imperial, don't go over 2 decimal places in inches, okay? So I'm just letting you know that that's accurate enough for deflections. So now I've calculated this deflection caused by the distributed load, and of course, what I want to do now, okay? Now, like I said, I have formulas that can calculate the deflection at this point here, at any point, but since I'm calculating the deflection at this midspan, I also want to calculate right here for this load, okay? Now, so here what I have is I have a beam that is simply supported, that's got a concentrated load, right? And it's somewhere along the span. And of course, then I can go look for a diagram that has something similar to my diagram to see which formulas I can use. And as we've done before, as we've done before, we go to beam formulas. Okay, and let me just put here, put this back to the page. Okay, so I'm coming down and you can see that there's quite a few choices you have depending on, So these are all, when they mean simple beams, that means it's all simply supported. In other words, you have a pin and a roller. That's what they mean by a simple beam. And of course, this is not your case, this is not your case, this is not your case. And of course, this is not your case, okay, because this is when the load is right in the middle, and therefore this would only apply when it's loaded in the middle. And of course, this is what you have. So in other words, we will be looking at this diagram here. Now, regardless whether P is on this side or on that side, these formulas are valid as long as the A value, okay, X, wherever you're looking for a value along X, as long as it's less than this value here. In other words, from here to here, these equations are good. Now, if all of a sudden the A value is less than the X value, remember you just have to like do the mirror image of A and B, and you'll end up getting the same thing. In other words, if all of a sudden my load would happen to be here, right? And I'm trying to calculate the deflection here, X, okay, right at the center. Well, X now is greater than A. Therefore, what you would do in that case is that in that case, you make this your B value and you make this your A value when you're using the equation. So in other words, you just take the mirror image of this diagram and just flip the A value for B and the B value for A. That's all you have to do. And you will be respecting the constraints that are given here. So all of these constraints have to be respected, okay? So like here, for example, so you have to make sure A is less than B if you want to use this equation, and then A is greater than B if you want to use this equation, and so on and so on. So keep in mind that you have to respect the constraints that are given here in these formulas in order to be able to use these equations, okay? Or these formulas, whatever you want to call them. So here we have it. So therefore, I don't want to calculate it right where the concentrated load is. In other words, delta at the point load. No, I don't want this. I wanted to calculate somewhere along X when X is less than A, because basically I'm trying to go to the center here. So since I'm going there, that means I'm trying to calculate the deflection from there to there, and that's X. And in this case, my X becomes L over 2, of course, which is 2,500. And my A is still greater than my X in my situation. Therefore, this will become my B value, and I can get that straight from my problem. And therefore, I will be using this equation here to calculate the deflection right at that point there, which corresponds to where I calculated for the distributed load. So that's it. So there's my equation, okay, PBX L squared over B squared X squared, okay? And again, there's my A value. My X value is at the midspan, 2,000, so X is less than A, so I don't have to modify anything here. Therefore, that becomes my B value. And therefore, I put in all the numbers. And again, be careful with the units, okay? And remember, since you are talking about newtons per millimeter squared, this has to be converted to newtons. And if you don't multiply it by 1,000, well, your deflection is going to be off by 1,000. You know, so that's why the units are very important. And I still carry my units after 40 years of practice. I still carry my units today because it tells me if I'm on the right track or if I'm out in left field. So I do strongly suggest that you get into the habit of doing all your calculations with your units, because it's going to tell you if you have to end up with oranges, if you're going to get oranges at the end of the day. You understand? So here we go. Here's all the values. So in other words, that's my P, but converted to Newton. B is that number there, 2,000. X is where I want to find the deflection for at midspan, 2,500. L is the span. B again is the distance from the right reaction area to the load. And X, of course, is where I'm calculating my deflection. L, the span, everything else. And of course, this is in newtons per millimeter to the fourth. So if I cancel all my units, I should end up with millimeters. And that's what I'm hoping to do. And therefore, so this, and this would cancel this. That cancels that. That cancels that. So I end up with millimeters. Fantastic. I can go on. And of course, I get 16.6. So that concentrated load causes a deflection almost equivalent to the distributed load. That's just a coincidence. It's not because of the, it's a coincidence of the magnitude of the force and where it's being positioned. And then of course, the total deflection is the deflection caused by the distributed load plus the concentrated load. So I add them both together because I can do the algebraic sum because I've calculated them both at the same position along the span. And I end up with 33.3 millimeters. And I think most of you got this bang on. So thank you very much for doing so well. Any questions before I move on to the second problem? Or is it clear? Is it okay?
Yes, sir.
Thank you.
Good.
Thank you. Okay, now this was the second problem. Okay, now here, what's nice about this here with this theory or the principle of superposition is that I can take something that is statically indeterminate, such as this continuous beam here, and with the formulas that I have, I can actually figure out and solve and analyze this beam. Okay, and of course here what we're doing is we're saying we have 1, 2, 3, 4. In other words, if I look at this, I have one unknown here, one unknown there, I have one unknown there, and I have one unknown there. And since I have 4 unknowns, I cannot use simple statics. In other words, I cannot use sum of f of x, can use sum of f of y in some of the moments to solve for my reaction areas. And therefore, I won't be able to solve this beam using simple statics. That's what we're saying, okay? So now, so what we do in this case is that we treat this beam and we remove the support here. And by removing the support, we will create a simply supported member. And therefore, with simple statics, I can calculate, of course, whatever I need to calculate. And and basically what we're trying to do is we're trying to say the concept here is very simple for me in a way. And when I saw this the first time, I thought this was ingenious, guys, okay? So basically, what you're doing is you're saying to yourself, okay, let's assume the beam goes from there to there, okay? And we remove that. In other words, we'll take this off. And I know that this here, okay, this here is going to cause a deflection like this, okay? And so here, right at this point here, I'm gonna, if I'm able to calculate the deflection here at this point here, okay, is it possible for me to apply a load on the other side that will bring this deflection back to 0? In other words, is it possible for me to calculate a load here that would cause an equal deflection here that will be equal to that one? And if I can, I know that this is the force that is required to bring this back to 0, and therefore that's going to be the value of the reaction area here, P. And I thought, when I saw this the first time, I said, whoever thought of this was really, really on the ball, okay? And that's what we're basically doing. So, and of course, with the beam formulas, it can simplify our lives on how to calculate this deflection here caused by the uniformly distributed load. Also calculate what force I need here to bring this deflection up to equivalent to that one, and then I can actually solve for P. And when I saw this the first time, I said to myself, whoever thought of this was really on the ball. Okay, so basically that's what we're trying to do. Now, convert the continuous beam to a simply supported beam by removing support between each column. So in other words, we get rid of that. That's what we're trying to do. And we're saying to ourselves, okay. And then we say, now, if I can calculate the deflection right at that point there, okay, and of course this becomes X, and because I'm trying to calculate the deflection somewhere along the beam for a uniformly distributed load, and this, where I'm trying to calculate where the reaction was, 4 meters. Now, of course, what you have to be careful about, okay, and you have to keep in mind is that the span now becomes, the L now becomes 10 meters, no longer 4 or 6 meters, okay? So that's the only thing that you have to be careful about. And of course, this stays the same. And now, how do I calculate the deflection there? Well, if I go to the, calculate the deflection where the support was removed, and of course you go to the beam formulas, and what's nice about the beam formulas is if we go back to the very first one, to the uniformly distributed load, we have here, okay, I can calculate the deflection anywhere along the beam with this equation here. That's what this equation is telling me. Anywhere that I want to calculate deflections, okay? I can even calculate the deflection at mid-span with this formula. It's just that it would be much longer. And if you put L over 2 into this equation, you'll end up with this equation, okay? So you can calculate anywhere along the beam, you can calculate the deflection, okay? And therefore, this is the equation I'm going to be using. And of course, all I need to know is the uniformly distributed load. I need to know where I want to calculate my deflection. And of course, the EI, I'm not too worried about, because when I calculate the other one, the EIs are going to cancel. So I don't even have to worry about those. And therefore, that's the equation I'm going to be using to calculate deflection right at 4 meters from the left support. Okay. So here's my equation. W is, of course, uniform, and then that's where I want to calculate the deflection. And again, guys, just be consistent, worry about your units, and you shouldn't have a problem solving, okay? Now, here, this is my W. X is where I want to calculate, and of course, the span now became 10 meters instead of 4 or 6 meters. And therefore, I put everything here, okay? This is my delta X. And of course, I simplify it to 124 kilonewtons over EI. Now, determine the concentrated force that would cause an upward deflection where the support was removed. In other words, so what kind of force do I need to be able to create the same equivalent upward displacement? And therefore, now, of course, I'm sort of say, like, what force can I apply here to cause a deflection equal to this deflection here? That's what I'm trying to do, okay? And therefore, I know that even though it looks like the forces underneath doesn't matter, it is still a simply supported beam with a concentrated load. And the only difference is that instead of being on top, it's going at the bottom. Therefore, everything would be reverse. And that's what you want to do. So basically, you go to your beam formulas. Okay. So here, all of a sudden, you go to your beam formulas. And of course, you go down and you see that it's the same one that we had before. Okay. The only difference is that now we're trying to, our P force is on this side. Okay, our P force is on this side instead of being on that side, but it's exact, and then our P force is underneath instead of, so I can use these. I just have to remember what the constraints are here. Okay, X has to be less than A, and so on. So I can use these. And of course, here I am actually trying to calculate deflection at the point load. So in other words, this is the equation that I'm going to need, okay, at the point load. And therefore, in other words, in our case, we're trying to calculate the deflection. If I put this the other way around, I'm trying to calculate the deflection at the point load here. Okay. Now you'll notice that in this case here, okay, there are no restrictions on whether A has to be less than B and so on. So therefore, you don't have to worry about it. Okay. So this becomes your A value. This becomes your B value. Okay, and so on. And that's where you're going to be applying the load. So here's our formula. PA, okay, so A is 4 meters, B is 6 meters, okay. EIL, of course, is the span, 10 meters, and therefore A is 4 meters, B is 6 meters, L is 10 meters. Now just be careful, put everything here, okay. And now I'm going to just want to simplify the deflection at A. Sorry, I got this pop-up that came up, okay. P 19.4 meters squared EI. Now, as I said, the displacement out of support is 0. So in other words, it will not go down, it will not go up. So what you did is you artificially calculated what it would be going down on a distributed load. You artificially calculated what it would be going back up to give you an equivalent force to bring you back up. And therefore, the way you can look at it is say the sum of the displacements should be 0. So therefore, you know the deflection caused by the concentrated load has to be equal to the deflection caused by the distributed load. And that's why you can equate the two. Mathematically, that's what you're doing. And therefore, you're saying delta X is equal to this, so that is equal to that. And then, of course, you put everything in terms of P. The EIs cancel, so that's nice. And therefore, I get 124 over 19.5. And of course, this cancels, that cancels. I end up with 64.54 kilonewtons. So that's the reaction force. So once I know the reaction force, well, I put it in my problem. Now all of a sudden, all I have to do is calculate the left reaction and the right reaction. I know in this case here, the Rx is equal to 0. So that's already 0. And here, unfortunately, compared to what I was telling you when we were doing moment diagrams, here, if you screw up on this value, there's no way of checking if you made a mistake or not. In other words, you cannot take moments about anywhere on the beam to see, because if this value is wrong, even if you take moments, you'll still end up with 0. So in this case here, the only choice you have is don't make a mistake in calculating this. okay? Because if this is wrong, the other two are going to be wrong, and therefore, and you will have no way of checking. So it's very important that this is correct. So if I take moments about the right, about here, of course, like I said, take this to be positive, and of course this is negative. Again, okay, just so that you guys, just to review okay, whenever you're taking moments about a point, the first thing you worry about is the sign, then the force, then the distance, okay? And what I should have done is I should have put these in square brackets, so maybe it would be a little bit clearer for those of you that are still having problems with this. But so this is negative according to my sign convention. Not that it's a negative moment, because I'm saying anything that's turning this way is positive, anything that's turning this way is negative. So this is positive, and this is, of course, is negative. So therefore, and of course, this is negative, and this is positive. So therefore, I worry about my sign, my force, my distance, my sign first, then my force. This is my force, and of course, this is my distance. My sign first, my force, and my distance. And then once all of these are equate, then I could equal to 0. If I screw up on one of these signs, of course, I'm going to be making another mistake. And once I do this, I have no choice but to say that this is 11.25 kilonewtons. Now here, like I said, this is the only time I'm going to tell you, do what they taught you in physics to calculate the other reaction. Use sum of f of y's. It's the fastest way to do it, because there's no way of checking whether you made a mistake or not. And all of a sudden, sum of f of y's gives me the reaction at ry, and ry ends up being 27.14. Because whatever value you put here, okay, you're going to, how can I say, carry that error into this one, and then that error is going to get carried into this one. So you won't have no way of being able to check whether you made a mistake or not, okay? The only other way is that once we learn how to use the software, we can model this in the software and see if the software gives us exactly the same value. Understand? We can do that, like when we start learning the software. As a matter of fact, I think we're going to start using the software next week. Okay, I hope you guys were able to download ADA, and for those of you that didn't, I hope you have access to the lab. And those of you that are relying on the lab, like I said, I would rather you have the ADA on your computer. And at the end of the course, I'm going to take a little survey of who did and who didn't have the ADA, because I believe we're going to be starting ADA next lecture. Okay. So this will be the last lecture where we're going to be doing things manually, like by hand calculation. After that, it will all be done on the computer. And that's it. So guys, and then of course, you show all your reactions here properly. And then once you've got your reactions, of course, you can do your shear diagram, and you can do your moment diagram, and so on and so on. And of course, without these, you can't do anything. And I don't ask you to do the shear diagram and the moment diagram. That's something that you should have been learned well in your physics class. I mean, I do a bit in this class. We will be doing a lot of shear and moment diagrams, but we'll be using the software to do those calculations for us. So is this all good? We're all clear? Because of course you're gonna have a typical problem like this on the next test. So I hope this is clear, and that's it. Okay, so if we're all good, any questions before I close the assignment? No? Okay, so now we might as well get into the lecture then. Okay. Do you guys remember doing the moments of inertias last year and all that? Finding centroids in your physics class? Is anybody out there?
Yeah, we did the moment of inertia and everything.
So, yeah, but I kind of forgot some of them.
Okay, in other words, you did moments of inertias. You did what else did you do? Like you did finding the centroid, the neutral axis, and all that. That's all the kind of stuff that you did last year, right? In other words, this is, for example, what you have here. Okay, so what you did manually last year, okay, is I don't know if you had. Okay, so last year, for example, you found where the neutral axis was for a particular shape. You did that, right? I'm assuming, or okay. And did you found moments of inertias, and you found the section modulus, and did you find the radius of gyration? Did they show you how to do all this?
Yeah.
Okay, so there, okay. Now, of course, what you have here, for example, okay, what you have here for very typical geometric shapes, these, I'm going to just expand this a bit. So you, okay, so these are, you know, these are like, you're going to get a copy of this table. Okay, you find this in most handbooks. Okay, so for example, if I have a square and I want to know the area, well, I just take D and I square it. If I want to know where the centroid is here, I take half of D. If I want to know the moment of inertia with respect to the centroidal axis, this is the formula. If I want to know the section modulus, if I want to know the radius of gyration, so here are the formulas. So what I like about these tables is that if you get into a complex geometry, you can break it down to different shapes, and of course you can sum them all up, and you can use the parallel axis theorem. I'm sure that you learned how to do, and you're able to, you know, come up with the total. And we're going to be reviewing some of this, because what I'm going to be showing you is that how do you do it. For example, what do you do in the case where I got a shape and all of a sudden I got a block of wood here, and I got a sheet of, I have a steel plate here that's going to be screwed to my block of wood. How do I convert this so I could be able to do my analysis based on the fact that I've got a composite material? And that's what I'm going to be teaching you in this class, okay? And of course, like for example, that's very typical. For example, you can have a steel beam here, okay? And all of a sudden you have a concrete slab, and you're going to want the concrete slab to act with the steel beam, and therefore you're going to end up with a composite section. And I'm going to show you how to calculate the properties of this. So therefore, if ever using ADA, ADA will not be able to calculate this for you. So you'll be able to calculate these properties, put them in ADA, and then you run your analysis, and it would be as if these values were already in ADA. And I'm even going to show you how to create your own section properties in ADA, okay? So that's what I'm going to be doing. And this here is just so, you know, like I said, the one that I use 99% of the time, the one that I use 99% of the time, of course, is rectangular shapes. So this is the one, you know, like the moment of inertia, BD, you know, BD cubed over 12. I know these ones like the back of my hand. I've been using, okay, those are, because those are the most common shapes that we use in engineering. And then after that, like, do I bother with these? Not necessarily. I simply, like, I use the different ways, you know, like using the parallel axis theorem. I don't know if you guys remember what I mean by the parallel axis theorem, where you get the, you know, I is equal to the moment of inertia with regard to the centroid plus the area times the distance squared from the centroids of each element to the central centroid. I don't know if you remember this, what I mean by the parallel axis theorem, okay? So in other words, if I didn't have these formulas here, if I can calculate this, if I can calculate this centroid here, and I can calculate this centroid here, and I can calculate this distance here, and I can calculate the moment of inertia of this, I can then use this formula here to get the value of I. Okay, so that's what I can do. So that's why I don't bother learning these other formulas. So these, like I said, these are nice little, you know, tables that give you, you know, so you can break down. And then of course, if you have a circle inside your thing, this is all the formulas for the circles and so on, triangles, parabolas. Okay, if you get into a parabolic shape, I mean, this is nice to know. If you have a trapezoid, a circle, okay, half a parabola. If you have a hollow circle, this is nice. Like whenever you're doing something with pipes, especially concrete pipes, this is a very nice thing to know. Okay, so you can do different things with this and so on. Okay, so you're gonna get a copy of this. Okay, so this is like, I copied this out of my steel handbook so that you guys can have this information if ever you get into something. And if you don't remember your equations completely for each small geometric shape, you can come to this table here, and of course you can get them straight from this table here. So this is, and of course these are the descriptions of what we mean by neutral axis. Okay, the line in any given section of a member subject to bending on which there is neither tension or compression. Okay, and that's what a neutral axis is. In other words, there. Okay, so that means that if I have a beam, okay, if I have a beam, okay, if I have a beam, and I find the neutral axis, And of course, in this case here, assuming it's isotropic, in other words, homogeneous isotropic section, and I can find the neutral axis here. Oh, sorry, I'm using the wrong. Where's the eraser? Okay, line. And if I can find the neutral axis here, okay, that means at this point here, all the stresses here are 0. Okay, so that means if I have a beam and it's being supported here and being supported here, and I need to make a hole in my beam where I know it's going to affect the beam as little as possible. If I make my hole here, it's going to have very little consequences on the strength of my beam because the stresses here are almost 0. If I make my hole here, it's a different story. So that's what's nice about knowing about the neutral axis, is that where can I make my holes? So when it comes to bending, these are the fibers that are going to be resisting the bending. So therefore, anywhere that you do around the neutral axis will not affect this, and it will have very little consequence on the strength of your beam. It can have a bit of a consequence on your moment of inertia, of course, and it can affect your deflection, but as far as the strength of your beam goes, it's going to give you the same resistance. So that's what's nice about knowing where the neutral axis is. And of course, the moments of inertia, the sum of the products obtained by multiplying each element of the area, which is a section is composed by the square, the perpendicular distance of the game. So in other words, what this means is that the moment of inertia is equal to an area times a distance squared. Now, guys, when I learned this the first time, I don't know if you guys realize this, okay, but the first time I learned this, in other words, the moment of inertia is equal to some area multiplied by some distance squared. So area is in squared, this is squared, and all of a sudden we're talking about to the 4th. I don't know about you guys, but I've had a lot of wine in my days and I still can't see the 4th dimension. Pretty amazing, okay? And that's what you have to appreciate when you talk about moment of inertia. It's purely an abstract concept, okay? Physically, I've never seen moments of inertia. All I know is that when you're talking about the 4th dimension, well, if somebody can draw me the 4th dimension, I'd like to see it to this day, okay? And therefore, in a sense, so that's what I found amazing about the moment of inertia. It says, wow, a purely abstract concept where the guy was able to calculate that this area here and this area here, okay, with respect to a distance here squared, I can calculate a moment of inertia, which will give me how stiff this beam is going to be. Pretty smart guy, okay, that did that based on mathematics. And of course, the section modulus is related to the moment of inertia, where you can calculate what the stresses are, okay? So in other words, what this does is, for example, if I have a beam that's bending like this, and all of a sudden I want to know what the stress is here in compression, I want to know what the stress is here in tension. Well, what this form is going to do is if I take a cross section across here, it's going to tell me that the stress is the highest at this point here at the outside of the beam, the stress is highest at this point here at this side of the beam, and of course at the neutral axis, it's going to be 0, and therefore I can actually calculate the value of that stress. So if I know, for example, my moment, and if I know my section modulus, I can actually calculate the stress at that point in the beam, okay? And of course, what moment of inertia is, what's S, okay, is equal to I over C, okay? And that's what it is for rectangular, and therefore it's very easy to calculate the section modulus for rectangular, since it's the distance from and this is the C value. Now for rectangular, C is the value from the neutral axis to the outermost fiber. And this is one that's really, I found this really interesting. I mean, I don't know if you guys find this interesting, but the radius of gyration, okay? This is, of course, very important when you talk about compression members, okay? The perpendicular distance from a neutral axis to the center of gyration. In other words, where things will start gyrating, in other words, rotating, okay? The point where the entire area is considered to have the same moment of inertia as the actual area. The square of the radius of the gyration is equal to the moment of the inertia referred to, okay, blah, blah, blah. Now, the radius gyration, okay, is used to ascertain the load of sections that will be sustained when used in a compression or so. Where the radius gyration are very, very important is when it comes to compression members. It tells you like when is this member going to start buckling, and like how slender it is and how it's going to be affected by its slenderness, the ratio of effectiveness under support length, and okay. And then of course the easiest way you can calculate the radius gyration are another formula that you guys might want to consider is equal to the square root of the moment of inertia of your section divided by your area. And that's the radius of gyration. Okay. And of course, if you have an x-axis, this becomes Rx. And when you have a y-axis, you take the moment of inertia with respect to the y-axis divided by the area, and this becomes Ry. And that's the radius of gyration. A very important property value when it comes to compression members. It tells you, the slenderness of a material of a column, and how that will affect its overall strength. So these and then there's one more property they don't talk about here, and I'm not going to talk about it right now, but it's called the plastic section modulus instead of the this is the elastic section modulus S, and then you have another one called the plastic section modulus called Z. Okay, whereby Z is the whole thing. Like the S is the stresses caused at the outermost fibers. So this is the S value here, whereas the Z, the whole thing plastifies. Okay, so you don't have this triangular shape, you actually have rectangle and rectangle. Okay, and this is very easy to calculate. You take the centroid here, multiply by the distance, and you multiply by the area of the two, and you get your Z value. So like the tables don't have it, but they're not very, and that's something that you're going to be using a lot when you're doing structural steel, the plastic section modulus, because the steel can actually have the whole section plastified before it fails, depending on other criteria. So that's just a quick overview of what you guys should have been learning in physics. I don't want to bore you with this. And of course, we're going to be using these properties to calculate the section properties of the composite materials. So now, so here you go. Now, what we're going to be doing, of course, is transformation of a cross-sectional area. The transformation of a section is accomplished by changing the dimension of the cross-sectional area parallel to the neutral axis in the ratio of the elastic moduli of the materials. Okay. Now, I bolded and underlined. In other words, all you have to do is change one dimension in your cross section, and the one dimension that you have to change is the one that is always parallel to your neutral axis. Okay, and that's what you have to remember. Now, what is the okay? So you can appreciate that steel has one modular elasticity, wood has another modular elasticity. So as long as I take that ratio, I can use and transform my section into one material. That's what we're saying here. Okay. Now, N is the modular ratio. Okay, and of course we'll use that's just a variable. And what is N? Now, guys, remember this. This is so you don't, okay. When you're calculating N, remember what goes in the numerator and what goes into the denominator. Okay, so modular elasticity material to be transformed. Modular elasticity of the section. So for example, if I have wood here, this is my wood. Let's say this is my wood. Okay, and I have a steel plate here. Let's say I have a steel plate there and a steel plate there. Now, if I want to transform everything into wood, and therefore, if I want to turn this into a whole wood section, therefore the wood will go at the bottom and the steel will go on the top. If I want to transform all of this into steel, then what's being transformed goes here, and what you want the section to be goes into the numerator or the denominator. So keep that in mind. Okay. That's how you have to remember. What am I transforming the material? I'm changing it from what to what? From steel to concrete, or from concrete to steel? And that's what you have to remember. Very important when it comes to this N, like which one you put on top and which one you put at the bottom. So that's number one. Now, after that, if a beam, okay, in a beam with a transformed characteristic, stress and strains, okay, vary linearly from the neutral axis. Okay, so just like it doesn't, once you've transformed it, everything stays the same as if it's one material. Okay, that's what they're trying to say here. The stress is calculated as the usual manner as, okay, are correct for the material on which, and now I'm going to show you what this means with the example. In other words, If you're calculating everything to wood, you can calculate the values of the stress in the wood right away. But if you're calculating the steel, you're going to have to multiply that by the N value to be able to get the actual value. And you're going to see this in the example, how that's applied. So that's the only thing I have to be careful about. So here, now, I'm going to do this example here so you guys can get the gist of what we're doing, okay? Now, the beam is subjected to a bending moment of 30 kilonewton meter around the neutral axis, the horizontal axis, okay? In other words, it's bending this way. What is the maximum stress in the steel? Here, okay? So in other words, now, I have wood and I have steel. So since I want to know the stress in the steel, I will convert, I think I converted everything into steel. So here, so the modular elasticity of the wood is 10,000 MPa, which is a reasonable value. Okay, and look at the modular elasticity of the steel, 200,000 MPa. So you can appreciate that the steel has it has a stress-strain ratio that is 20 times better than wood. Okay, that's what you should realize here. Okay, so in other words, if anything, it's going to deform 20 times less under the same stress or under the same strain. The wood will deform 20 times less. That's what you should be understanding from this. Now, transforming the cross-section area to steel, because I want to know the stress in steel. So that means that the numerator becomes the E for wood and the denominator becomes the E for steel, okay? So the N value is the modular elasticity of the material to be transformed. So in this case, I'm transforming wood to steel. And of course, the modular elasticity of my cross-section, which I want to have as the overall one material. So here I have 10,000 divided by 200,000. Of course, I end up with 0.05. And of course, there's no units because it's a ratio, okay? So there's my N value, okay? Now, as I said before, you transform the dimension that is parallel, okay, parallel to what you want to transform the section to, and therefore, in this case, we want to transform it parallel to the horizontal axis, and therefore, I will take this dimension here and transform it into steel. So multiply the dimension of the cross-section parallel to the neutral axis by the ratio modulus n to transform the cross-section. So you only change one dimension, not two. And that dimension is the one that is parallel to the neutral axis about which you want to do your calculations. So in this case here, it's very simple. I got, this is, okay, my neutral axis is here, okay. The dimension that is parallel to the neutral axis is the 150, and therefore this is the one I'm going to be transforming, not this one. Okay, and therefore, so therefore, this is no longer 150. The equivalent of this wood to steel would end up being only 7.5 millimeters thick. In other words, it's going to be 20 times smaller than it actually is. So that's what that would represent, that amount of steel, had that been steel in the first place, okay? So that's how I transformed this. Now all of a sudden I have, so in other words, this wood piece ended up being 7.5 millimeters. So now, because I transformed the wood into steel, this is as if it was a steel section all by itself, because I've used the moduli ratio to transform the wood to steel. Now that I've got everything in steel, well, just like you did in your physics class, you have to start calculating some sectional properties. And then, of course, the first properties you have to calculate is the neutral axis. So now the stress in the steel, okay, M is divided by the section modulus. I know last year they probably gave you this equation. The stress is equal to the moment, bending moment times the centroid divided by I. That's what they probably gave you for the flexural formula. But remember that S is equal to I over C, and therefore we don't use this in engineering. We use the section modulus, okay? And therefore we calculate the section modulus, and we know that the stress is equal to M over S, and that's what we use, okay? It comes out to the same thing, but it's much easier because the books will give you the value of S in your steel and so on, okay? So I don't know if they covered that also, but that's what we're going to be doing here. So now, of course, to calculate the S, what we need to do is, of course, the stress is equal to the moment, the bending moment times the section modulus. And I think in this case, I gave you what the bending moment was in the problem. And if you didn't, well, you would be able to calculate the bending moment from, like either, your bending moment diagram. And then, of course, once you calculate your S, you'll be able to do this equation. So now, the elastic section module S, okay, I divided by C. In other words, C is the distance from the C is the distance from the neutral axis to the outermost fiber. Okay, and of course here it's not symmetric. So the first thing I need to do is determine where the neutral axis is. Okay, so S is equal to I over C. Okay. So the neutral axis is a line in any given section of a member in which there is neither tension or compression. Okay, of course, and that's what the neutral axis is. And C, of course, is the distance from the outermost fiber to that axis. So what we need to do, determine the neutral axis of the transform section. So this, guys, should be more of a review. Okay. Now, I don't know how they showed you this in physics. Okay. But you can do two things. Okay. Now, I like to use tables. I don't know if you guys use tables. I like to use tables, and you can do this a number of ways, guys. I don't know how did they show you to find a neutral axis in physics, guys? Because I might use that so that you don't get confused. Can anybody tell me?
I think it was tables as well.
You use tables as well? Okay. So you're familiar with the tables? I just want to know, because I don't want to.
Yeah, we use tables.
Okay. Now, I don't know if they explained this, but the first thing you have to establish when you're trying to do this is what? Tell me.
To find the area of the section.
Well, the first thing you determine is you have to break down things into different areas so that you can work with them, right? Number one. Okay, so in other words, this will be my area number one. This will be my section one, which I call section number one, and this will be section number two. Okay. What's the second thing you have to establish?
Where the center line is?
I know, but before you establish where the center line is, what do you have to determine? Like, what do you have to fix as a constant in this problem? So the first thing you do is you take and you break down the thing into very simple geometric shapes that you can work with. That's number one. Okay, in this case, we only have two. We have section one, section two. What's the second thing you have to establish? Does anybody remember? Any suggestions? Why did I put 5 here?
That is the neutral y-axis of section 1.
That is the distance from the centroid of section 1 to where?
To section 1?
Yeah,
No.
but why did I put 5? Okay, why did I put 135 here?
That is 260 divided by 2 to get the 135.
In other words, what'd you do to get 135?
So is that the distance from the x-axis?
The x-axis. No, if it would be the distance from the x-axis. Yeah, okay, the distance from the x-axis, exactly. But now, why? In other words, are you telling me that this is the x-axis?
Yeah, I'm not
Okay,
sure.
so don't call it the x-axis, call it an axis Okay, a reference axis. Okay, you can call it X because we tend to, because we're moving along the vertically, we call it Y bar if I'm moving. Okay, so first thing, the second thing you have to establish is where are you going to take all your reference points to? Okay, in other words, you need a reference line. Okay, now guys, I can tell you right now. Okay, close, clear the drawing. Okay, so what I tend to do is, for example, I took it here, right? In my case, everybody understands? Would I be allowed to take it up here instead of down there?
Yeah, you could.
I could. I can take it anywhere I want, guys. Okay, very good. I can take anywhere. It's just, that's the second thing you have to establish. Of course, you would establish where your calculations would be the easiest to do it with, okay? Now, would I be able, let me just clear this, okay? Would I be able to take it right here?
Yeah.
Okay, now if I take it right there, what's the consequence of me taking it there? Now, let's say that this was my reference. Okay, this is my reference axis, okay? If I take this to be my reference axis, what changes in my table?
The Y could be negative for section 1.
This would become a negative, and what happens for section 2?
It just becomes 125.
Exactly. Okay, so guys, that's exactly. So you guys are starting to understand. Like, in other words, you can do whatever you want. Just remember, if you're going away, like if you're going below your reference line, it becomes negative values. When you, in other words, the distance from your centroid of this section to your reference line becomes negative. So you can do whatever you want. Just that for me to avoid having these negative or positive, I tend to always keep everything positive. Everybody follows? Okay. Now do what you want, but that's what you're basically doing. And of course, once you calculate the area and once you calculate the distance from the centroid of that area to where your reference line is, this becomes your AY bar. Okay. And once you do that correctly, then of course, the neutral axis is your AY bar divided by your A, and that gives you your Y bar. Now, the reason why we call it Y bar is because we're moving along the Y axis. That's why we call it Y bar, okay? And that's the only reason we call it Y bar. In other words, we tend to call this the X axis, we can tend to call this Y axis, and we're trying to find a distance along the Y axis. So, I'm glad it's coming back slowly, okay? So now, so Y bar is AY bar over A, and therefore I end up with 77 millimeters from the bottom, because that's where I took my reference point, okay? Now, once I do that, okay, for example, would you believe that I can also do this? I can make this into one big square. I can do this, okay? And whatever I'm creating here, I just have to put negative values and I will end up getting the same thing, okay? So just to let you know, whatever you're, okay, so I don't want to confuse you, but there are, many number of ways, but I like to keep things so I can minimize. So I like to establish my reference line where I don't have to worry about positive or negatives. And of course, here, the only thing is that once I calculate my centroid here at 125, I have to remember to go to my reference line, I have to add another 10 millimeters to get to 135. So that's that. Now, once I've calculated my Y bar, well, there you go. There's my neutral axis. Now, what can I do with my neutral axis? Wow. With my neutral axis, now I can calculate my moment of inertia. You guys remember how to do that? Does anybody remember how to calculate their moment of inertia of this section, knowing where your neutral axis is?
No, sir, I forgot about it.
You forgot how to do it?
Yeah.
Well, in this case here, okay, you have to determine the moment of inertia of the transform section using the parallel. Did you learn about the parallel axis theorem? In other words, you take the moment of inertia of your section that you're calculating, and then you take the distance of that section, of the centroid of that section to the distance of your neutral axis, and you square it. You guys learned this in physics? Did you guys ever do this in physics?
Yes, we did.
Okay. So in other words, what this means is that if I can break down, like in other words, this is one section here, and this is one section there, okay? So in other words, if I can calculate the moment of inertia of that section there, that's what this is, okay? And then I can calculate the distance from the centroid of that section to the centroid of my overall section, which is, that's what this here, my D. And if I know the area of this section, and I multiply it by that distance squared, that will transform this into the overall. That will transform this section into the overall section of my cross section. So, okay, so you did this. It should be more of a review. So IC is the moment of inertia section with respect to the centroid of the section. Okay, so and then of course you got to remember that for rectangles it's very simple. It's 1/12 the base times the height or the depth squared. And remember, the base is always a dimension that is parallel to your axes, okay? And the height is always the distance perpendicular to your axes. So that's something else you should keep in mind, so you don't know which one is which. I've seen so many people switch that around. Now, A is a cross-sectional area, of course, and of course, here's my cross-sectional area, here's my cross-sectional area. So what I like to do, of course, okay, is, for example, if you guys want to know, okay, I'll show you what I do, and then maybe you guys want to do the same, but what I do, okay, I can't even see the bottom one here. Okay, D is the distance from, can you guys see the bottom of the slide on your screen?
No.
I can't see it either. Oops. Okay, can you see it now? D is the distance from the, okay, because for some reason, I don't know why it went that low. So D is the distance from the centroid to the neutral axis, okay? Now, so I'm going to continue with the slideshow. Okay, so basically determining the moment of inertia I, so here, okay? So here's my 77, this was 0.5, okay? So what I like to do is, of course, calculate the moment of inertia of section 1, the area, and then for the D, I simply take the distance y bar and I subtract this distance from it and I square it, okay? Now, for a rectangular section, you might not remember this, but basically, the moment of inertia with respect to the centroid is equal to 1/12 the base times the height for a rectangular section, whereby B is the dimension parallel to the neutral axis, and H is the dimension perpendicular to the neutral axis. So that's how you're, in other words, if I'm calculating moment of inertia with respect to this axis, this becomes my B, and this becomes my H, or you guys who can use D, it makes no difference. If this happens to be my neutral axis, then it changes completely. In other words, this becomes a B and that becomes a H. So that's what you have to worry about, in which direction you're calculating your section properties. And B is always parallel, H is always perpendicular to the axis about which you're calculating the properties. And that's what you have to keep in mind. Now, in this case here, I have 1/12 the base, which is 150. The height is 10, okay? Of course, the area is 150 times 10. The distance from this centroid to the neutral axis is 72 squared. And of course, I have to add this section here to it, 1/12 the base. Now, the base is the distance parallel to the axis, which is 7.5 in this case. And the height here is 250, that's H. And therefore, A is 7.5 times 250 times the distance from the centroid of that section to the neutral axis squared, okay? And when I do this, I end up with 23.864 times 10 to the 6. Now, guys, get into the habit, okay, always using the scientific notation when you're working in millimeters squared, okay? In other words, always, if you're doing your calculations, even on your test, I don't want to see 23,860,000. I want to see 23.86 times 10 to the 6. Get into the habit of putting it in this format, okay? Because that's how you're going to see it in all your engineering books when it comes to millimeters to the 4th. So use the scientific notation. In other words, whatever number you get out of here on your calculator, you get an astronomical number on your calculator, just say divided by 1,000 squared, and it's going to give you this value right away. Okay, so that's the easiest way to do it on your calculator. And now the section modulus is I over C. Now you got to be careful. You want to calculate the stress in the steel. So the stress in the steel is here. Okay, so this one, in this case, the section modulus would be the distance from here to here. Okay, if I want to calculate the stress in the wood, then I would have to take this distance here. Okay, so that's why I take 77. 77 is the distance from the neutral axis to the distance of the fiber where I want to calculate the stress from, and therefore I over C, and that's why I use 77 here. And I get a section modulus of 310 times 10. And again, scientific notation. Whenever you're talking section modulus, millimeters to the fourth, make sure you put it to the 10 to the third. In other words, scientific notation, 10 to the third, 10 to the sixth, 10 to the ninth, 10 to the 12th, and so on. In other words, multiples of 3, okay? So now I've calculated my section modulus with respect, and the reason why I say B here, because this is only good at the bottom, okay? And if I would be referring to this section modulus, I would call it ST, the top, because it would be different than the bottom, okay? So when the neutral axis is not right in the middle, in other words, if your section is not symmetric, then you have two section moduluses. You don't only have one. You have one with respect to the bottom, you have one with respect to the top. And of course, the distance is going to determine which one's going to be the highest one, okay? So since now I've got my I, I've calculated my section modulus, and of course now I know what my moment is. What I can do with this is I can go and calculate the stress, which is the bending moment divided by the section modulus. I take 30 times 10 to the 6 because I want to convert this to Newton. I had kilonewtons meters, and I have to calculate this newtons to millimeters. Therefore, I multiply by 1,000,000 divided by this, and I end up with a stress of 96.8 megapascals, which is not much for steel, because steel you can go up to about 350 megapascals. So this steel is not stressed very much, okay? So that's for the steel. Now, okay, now to determine the maximum stress in the wood, the elastic section modulus at the top end must be evaluated, and then the stress has to be multiplied by the ratio. So whenever you want to calculate the stress in the other material, you have to remember you have to multiply it by N, okay? So here we get, for example, so now the section modulus at the top would be the I over C with respect to the top. Okay, so now this all of a sudden this becomes 1. In other words, it's whatever this is, 235 minus 77, that gives you the value here. So 183, I should have put it on my diagram. So the distance from here to here should be 183 if I didn't make a mistake in my calculations. There's my C value, because I'm looking at the stress right there. And of course, the section, the moment of inertia does not change. That's the same for the overall section. And now if I want to calculate in the wood, okay, I calculate M over ST, but I have to take this value and multiply it by N, okay, to transform it into an equivalent wood stress. And therefore, I end up getting 230 times 0.5. And now the stress in the wood is 11.5 MPa, which is a little high for the wood, I can tell you right now, okay, but it's still okay, okay? And that's how you would calculate the stress in the wood. So you have to remember that when you calculate the material the stress in the material that has been transformed, you always have to multiply that by the N value, okay? So, and that would be it. Now, what I'm gonna do is I'm gonna redo this problem, but I'm gonna flip it around. Okay, I'm gonna now say, let's change everything to wood and see if we get exactly the same results. Okay, and that's what's interesting about this. I wanna do this, okay, with you. And of course, you'll see that there are gonna be a lot of similarities, okay, in the values.
Excuse
Now,
me, sir.
yes.
Can you go back to the last? I was wondering what is M.
N is your M, your bending moment. I gave you that at the very beginning of the problem. Remember, I said this beam has a bending moment of 30 kilonewton meter.
Oh, okay, yeah.
M is your bending moment, okay? Like I gave you the value of M, but you know, if you're actually doing a problem, you actually calculate the bending moment in your beam, and then that will be your M value, and then you have to calculate your section properties.
Okay, I see, thank you.
M is the bending moment, okay? Sounds good?
Yeah.
Okay. So like I said, I mean, this is your flexural formula. Yeah, you know, last year, like I said, last year they probably showed you, I don't know if when they teach you the flexural formula, they said the stress is equal to the bending moment M divided by the centroid distance divided by the moment of inertia. This is what you probably saw in your physics class, right? If you don't remember, but it's okay. And what I'm saying is that the value of the section modulus is I over C, and therefore we tend to replace, and that this C cancels that C, therefore you get the stress is equal to M over the section modulus. Understand? And that's why it's easier to calculate your stress based on the section modulus. And I don't know why they don't teach you that in physics. You know, anyways. So here we go. Now we're going to go and do the same thing, except now we're going to be transforming everything into wood to see if we get the same values in terms of stresses. And in theory, we should, okay? Now, the thing that I want you to look, the thing that's interesting, okay, is that first of all, I'm transforming the section to wood. That means I'm going to be transforming the steel into wood, and I'm going to be transforming the dimension of the steel parallel to the axis into wood. But before I can do that, I have to calculate now the equivalent, the modulus, okay, the n value, the ratio. Now I take the modulus of the material to be transformed, in this case is steel, divided by the modulus of what I want to transform the whole section, in this case is wood. So therefore I would take 200,000 MPa for the steel over the 10,000, and then now I get 20 instead of 0.05, okay? So that means that I would take the 150 here and multiply that by 20. In other words, I transform only the dimension that is parallel to the axes that I'm transforming calculate my section properties to. So you multiply the dimension of the cross-sectional properties to the neutral axis by the modular ratio n to transform the cross-sectional area. Now, so that means that this is going to be 20 times bigger, and of course that comes out to 3,000. So the equivalent width of the wood is 150 times 20, gives me 3,000 millimeters squared, okay? And this is what you're looking at. Okay, so this now becomes, the height doesn't change. You only change the dimension parallel to the axis about which you're calculating the section properties. So here this becomes 3,000. This stays to 10. This stays to 250. And of course, this stays the same to 150 on top. I didn't put it here. Okay, but you have the 150. So now that I've transformed the dimensions into an equivalent wood section, now of course I can go and calculate the section properties. So now to determine the neutral axis, just like before, okay? And believe it or not, what's really amazing here is now, of course, the difference is that the areas change, these stay the same, okay? But the thing that you'll find amazing is, guess what? Where do you think the neutral axis would be in this case? Does it change? Do you remember where it was when we transformed it into steel? When we transformed this into everything into steel, we had a neutral axis of 77 millimeters from the bottom. Look at this. When we transform everything into wood, guess what? The neutral axis is 77 millimeters from the bottom. So the neutral axis will not change no matter what material you're transforming it to, okay? And that's, you know, and it should be that. That should be the case, okay? And therefore now I have exactly the same location for my neutral axis. Now, of course, that's the only thing that doesn't change. Your moments of inertia are going to change drastically because your areas are much bigger, okay? So the same as the value is number one, and that's exactly, in other words, the neutral axis is the same whether I transformed everything into steel or I turned everything into wood, and that makes sense to me, okay? And now, and that's the only thing that stays the same. The moment of inertia is completely different. Why? Because the areas are different, and therefore when you do your AD squared, your moment of inertias are going to be different, okay? Now, the only thing that stays the same is the D distance, okay, but everything else. So determine the moment of inertia of the transformed sections. Again, I'm going to use using the parallel axis theorem. Now, this is what I have. So in other words, I have, this is area 1, there's my distance. This is my area 2, there's my distance. And you'll notice that these distances are exactly the same that we had in the first problem, okay? And the only thing that really changed is the areas, and of course the moment of inertia of each section, because this becomes 1/12 the base times the height, which is 3,000. So therefore I get 1/12 the base. And like I said, so that I'm going to repeat it again. people have asked me, which is the B value? The B value is always the one that is parallel to the axes that I'm calculating my section properties. So therefore, this becomes the B value, which is the H or the D value, always the one that is perpendicular to the axes, and therefore this becomes my D value. Okay. So now, so I get I is equal to 477 times 10 to the 6. Of course, the I would be astronomically bigger because the areas are astronomically bigger. Okay. And the section modulus now, believe it or not, becomes at the top because I'm trying to calculate at the top for the wood. Okay. And therefore, if I do this, but the thing that's amazing is that, of course, whether I do it this way, the stress is exactly the same as I calculated when I transformed everything into steel. But now I don't have to multiply by N because everything is into wood. Now, if I want to calculate the stress into steel, I have to multiply the section modulus stress by the N value. And therefore, okay, so I have exactly the same value as I had when I calculated the stress in the wood in the previous problem. And now, okay, for some reason, this menu here is interrupting with the slide. Okay, the same as example number 1. Now, determine the maximum stress in the steel. Now, remember, okay, that it has to be multiplied by the modular ratio. Okay, so therefore, I do the same thing. I calculate it with respect to the base. So this becomes the section modulus of the base here, SB. In other words, the moment of inertia that I calculate divided by the distance. This gives me the SB, the section modulus with respect to the base. Now, when I do the calculation, I get this. And if I multiply by N, which is 20, I get exactly the same value for the stress in the steel. So what's nice about this is that you got to remember, you can use these no matter which material. You would normally transform it to the material that you think is the one that you're really, you might have to, you want whatever is more convenient for you. But remember, whenever you're calculating the stresses, that whatever properties you calculate from the transform section, you don't have to do nothing. Those are directly given from the formulas that you calculated here, but when you're calculating the other material, always remember to multiply it by N, okay? And in this case, N is 20, and therefore I end up with the same value. So I'm just trying to show you, it doesn't matter which way you go, you should always end up with the same stresses and should always end up with the same neutral axis. But as far as the section properties, the S and the I, that's going to change totally because your areas have been transformed into the equivalent material. Okay, same value as number 1. Okay. Any questions on this? Is it clear? I know like you guys are juggling your memories, but now, I don't know if how many examples I have here. Okay, here's a typical, okay, here's a typical, okay, situation that you have when you're designing a highway overpass. In other words, in a highway overpass, you use these steel girders, and to take advantage that you're putting a concrete deck on top of your steel girders to create the roadway, okay, you're going to want the concrete to work compositely with your steel. And what you're going to see very often, okay, next time you guys happen to see an overpass being built and you're driving on the highway, and if you can see the girders, you're going to see the steel girder, and on top of those steel girders, you're going to see these are called studs, Nelson studs, and they're shear connectors. They make sure that the shear flow between the concrete and the steel does not slip. Okay, that's what, and they make sure that the concrete will work compositely with the steel. So that's what these things are. These are shear connectors, and there's ways of calculating how many you need and at what spacing and so on and so on. But that's going to be, you know, that's not going to be part of this course. So those, and therefore, this is a very typical situation where you would have to transform. And in this case here, what we do is we don't transform the steel into concrete. We always transform the concrete into steel. And by doing this, it allows us to increase the sectional properties, and therefore we can save some money in the size of steel that we need to build our highway, or even floors. You can do this with floors also, okay? Okay, so here is the problem, okay? The steel is subjected to a bending bending moment of 600 kilonewton meter. Okay, I'm giving you this, okay, because I don't want you, I could have given you a whole geometric shape and I said, well, this is where the supports are and we could have calculated the bending moment, blah, 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 but okay. Now, around the horizontal axis, in other words, it's bending about this axis here, okay. The modular elasticity of the concrete, 2,500 MPa, and of course, for steel, it's always going to be 2,000 MPa, okay. Now, this steel beam is a W530 by 66. Okay. Now this is the cross-sectional area of the beam, and this is the moment of inertia IX of the beam, of only the beam. Okay. And of course, the D here, the distance from here to here is 525. Okay. So you see here, when I was telling you that this designates the nominal depth of the beam, well, this means that the beam is approximately 530 millimeters. Well, when I went into my steel handbook, in my steel handbook, it will give me the actual depth of the beam. It ended up being 525. So it ended up being 5 millimeters smaller than the nominal depth. Okay, but in terms of geometry, it doesn't matter, but in terms of calculation, it might have a slight impact. Okay, so now, what we're going to do, of course, is that it's going to be much easier to take this rectangle here and transform it into steel than try to take this two plates and all that and transform all this into concrete. So what we're going to do is we're going to transform the concrete to steel and then do all our calculations. Okay, so transforming the cross-sectional area to steel. Therefore, I take the ratio of the material to be transformed, which is concrete, into the material that I'm transferring the cross-section to, which is steel. So therefore, I take the 2,500 divided by the 2,000, and I get an N value of 0.125. Now, that means that I only transform the dimension that is parallel to the axis. Everything's bending. I'm trying to calculate everything with respect to this axis here. Therefore, I only multiply this value by the N value. This stays the same. Okay. So now multiply the dimension of the cross-section area parallel to the neutral axis by the modular ratio N to transform the area. So this is what you're going to see. Okay, so I take the 1,500 multiply, and therefore the concrete shrinks from 1,500 millimeters all the way down to 187.5 millimeters. So in other words, this, okay, so in other words, if you're looking at all this concrete, this is what it would be equivalent to if it were steel. Okay, that's what you end up having it. So now what you need to do, of course, is just like before, you have to find out where the neutral axis is of this cross section. Okay, now what I did in my case is I said, okay, let me use this as my reference line right here, the bottom. Okay, and therefore by using this at the bottom, I know that this here is symmetric, and therefore I know the centroid here is right halfway through my D value, which is 62.5. And then I know that here the centroid is halfway through here, so it's very easy to calculate. Okay, so therefore it's 75 plus 525, which is 600. So the first thing I establish is where I want to put my reference line, number one. And then after that, calculate where the centroids are of the sections that I want to work with. And then after that, calculate the distance from the centroids to my reference line, and then I can set up my table. So that's the first thing I do, okay? So therefore, I said, this is going to be one section all by itself. And of course, what's the area? That's given to you from the steel handbook, okay? What's the distance here? Well, it's half of the D value, which is 262 divided by 5. And of course, it's simply the multiplication of those two numbers. Now, what's the area of this? 187 times 150. It should give you this value here. The distance here is 600. And then, of course, now the sum of the AY bar divided by the sum of the areas gives you where the Y bar is. In other words, the neutral axis. And therefore, AY bar is 19 million, blah, 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 cubed divided by the squared, and of course ends up with millimeters, and that's the right units from the bottom. So right now, my neutral axis happens to be just slightly below this point here. Okay. Now, determine the moment of inertia of the transform section using the parallel axis there. Now, for the steel, this is given to you already. In other words, this is your IX value. All you have to worry about is your AD squared for the steel. For the concrete, you have to calculate the IC for this. Then, of course, you have to calculate the distance from the centroid of this to the centroid of your cross section. So basically, IC is the moment of inertia of the section with respect to the centroid of the section. That is given to you in the steel handbooks, and I gave you that in the problem, so don't worry about it. And A is a cross-sectional area that's given in the handbooks for the steel, and so on. And D is the distance from the centroid to the neutral axis. Okay. So therefore, now, so here I have, like, guys, make yourself sketches and be clear on your sketches so that you can do these calculations. Don't do them in your head. It's the easiest way to make mistakes. So the first thing I do is, this is the centroid, okay? And therefore I calculate the distance from there to there, and then I calculate the distance from there to there. My neutral axis is all the way up here. That's what we calculated before. Therefore, that's the value, that's my D for the steel. There's my, I'm sorry, is that, hold on a second. Yeah, 522.6. So it's all the way up here, okay? I just wanted to make sure I didn't make a typo. So here's my neutral axis. I put my neutral axis in my cross section, and I actually calculate these distances very carefully. In other words, I take my neutral axis and I determine this distance here. I take my neutral axis and determine that distance there, so I don't make a mistake in calculating my moment of inertia, because if these are wrong, my moment of inertia is wrong, my section modulus is wrong, everything else is wrong. So I try to be very careful. So IC, of course, is 1/12 the base. So for this one, it's very simple to calculate. It's 1/12 the base, which is 1,187.5 times the height here. And therefore we have, okay, IC is 325 times 10 to the 6. This is the one that's for the steel, which is given to you from the steel handbook, okay? This is the area that you get from the steel handbook. I'll give you that in the problem. And of course, this is D squared, which happens to be the distance from this centroid to your neutral axis. That's D squared. And of course, here you need to calculate it yourself. So this is 1/12 the base, which is 187.5 times the height, which is 150. I should have put the height here. This, if you remember, this was 150 millimeters thick, 6-inch slab. And of course, the area, 187 times 150 times the distance squared, 77.4. And now I've got all my values. And if I calculate this, I end up, of course, like I said, scientific notation. I get 1,137 times 10 to the 6 millimeters to the 4th. That's the moment of inertia of this whole cross section. And now, since I know that, I can calculate the section modulus with respect to the bottom, because this is where the steel is going to get stressed out, okay, right there. And therefore, I can calculate with respect to the bottom. And of course, it's the moment of inertia divided by the distance from the neutral axis to the outermost fiber of your section here. Okay, this is it. So therefore, it's your moment of inertia that you just calculated here, divided by the distance from the neutral axis to the bottom of where the extreme fibers of the steel is, right there, 522.6, and therefore this becomes my section modulus. And if you notice, I always put it in scientific notation. Now, so now that I have my section modulus and I know my bending moment, I can actually calculate my stresses. Oops. So now I take, of course, you remember guys, this is kilonewton meter, and this is millimeters cubed. Therefore, you have to convert this into Newton millimeters in order to get MPa, newtons per millimeter squared, and therefore you have to multiply this by 1,000,000. If you don't do that, and I end up with 275.8 MPa, which is still very reasonable for steel, because steel can go up to 350 MPa very easily, and that would be the stress in the steel. So therefore, the beam that you chose would be adequately designed for the for whatever you need to support that caused that bending moment. Any questions here? I don't know what happens after this. Okay, now I wanted to do one more where we're going to be changing it about both axes. How are we doing time-wise? Okay, so I want to do one more where we're going to be changing about both axes so you guys can appreciate that depending on which way you want to do it. The composite column now, okay, is made up 2 steel plates, 1, 2, okay, and a concrete core. Transform the section and calculate, okay, with respect to the x-axis and the y-axis, okay, in this case. And then I want you to calculate the ix, the sx, and the rx, the iy, sy, and ry, because it's going to be a column. You're going to need to know the radius of gyrations. So therefore, you can calculate the slenderness of this column if ever you're going to be doing calculations. Now, the E concrete, I put a C here, is 20,000 MPa. So in other words, this must be about a 20 MPa concrete for it to be in that order. I know, I expect you guys to know that. And of course, for steel, we always assume the modulus elasticity to be 200,000 MPa in imperial, I'm sorry, in metric. So now, same thing. So what we're going to do is I say transform this section to steel. So we're going to change the concrete to steel, okay? So transform the area to steel with respect to the x-axis. I do it with one axis, and then I'm going to do it with respect to the other axis. So I have the modular ratio equal to E concrete over E steel, 20,000. Okay, so I end up with 0.10. And therefore, I multiply all the dimensions of the concrete that are parallel to the x-axis by 0.1, and therefore this will transform the concrete into steel. And therefore, I get 200 times 0.1. In other words, this concrete will now be coming down to this width here if I go and make this equivalent to the amount of steel of 20 millimeters. That's what I'm doing right now. So all of a sudden, I went from a 200 millimeter weight concrete, it went down to 20 millimeters. So now that I've got everything in the transform to steel, I can now calculate my section properties, okay? And of course, the cross-sectional, okay, now guys, the cross-section is symmetric with respect to both axes. Therefore, the neutral axis coincides to the center of the, so you don't have to calculate X bar or Y bar, because as soon as you find symmetry, you found where the neutral axis is. Does everybody understand that? Or does anybody have any questions? Now, don't waste your time. Like, for example, as soon as something is symmetric, okay, if this is symmetric, I can guarantee you that the neutral axis is going to be right in the middle. And if this is symmetric, the neutral axis is going to be right in the middle. So as soon as you find symmetry, if you find a line of symmetry, you found the neutral axis. Trust me, okay? So just to let you know. So in this case here, I know that my neutral axis is right down the middle. In other words, right right here. Right, there's my neutral axis. I won't even bother calculating it, okay? So now I know where my neutral axis is. I can actually calculate the Ix with respect for the whole cross section here, okay? And therefore, now guys, I'm gonna go through this slowly so that you guys can follow. So in other words, this is 2. The reason why I put a 2 here, because I have 1 here and I have 1 there. They're exactly the same. So I could just multiply each one by 2 and I'll get the same value. And then 1/12, the base, of course, the base is 200 here. There's 200. And the height is 10, and therefore there's the height, 10. So that takes care of the IC for the top and bottom flange of, okay, top and bottom flange, I call them flanges, but plate here. And then the area, of course, is 200 times 10. And what's the distance? Well, if this is 150 here, and this is 10, well, that becomes 155. So the distance from the centroid here to the axis is 155 squared. And that takes care of that one and that one. Now here, I only have 1/12. The base, of course, the base is always the dimension parallel to the axis, which is 20 in this case, and the height is 300. Why don't I have an AD squared here? When I'm doing this for this section here, why don't I have an AD squared?
You get one in the negative part and the one in the positive.
No, it's because the centroid of this section here coincides with the centroid of the overall cross section. So the distance is 0. D is 0, therefore everything goes to 0. Does everybody understand that? This is the overall section. Okay? The centroid is right here for the overall section. Where's the centroid of this section here? At the same place. So what's the value of D? The value of D is 0. So therefore, what is AD squared equal to? 0. And that's why we don't have any terms here. Okay? So since I don't have to transform this section, it coincides where the transform section is, I don't have an AD squared. Okay? So now, of course, I do this and I calculate the IX value. And then once I've calculated my IX value, of course, it's very easy to calculate the section modulus because I need to know the distance from here to the outermost fiber, which would be 120. So therefore, IC is equal to 141 divided by the distance. IC is the distance from C to the outermost fiber. So here it's 150 plus 10 gives me 160, and that's what I use here for C. And of course, it's the same distance, therefore I only have one section modulus because of the symmetry. And I end up with 882 times 10 to the third millimeter to the fourth. Now, the only thing that I told you this at the very beginning of class, but I don't expect anybody to remember this, okay? When you want to calculate the radius gyration, well, the radius gyration with respect to the x-axis axis, well, that's going to be equal to, okay? The radius gyration is a distance perpendicular to this, okay? And now that's for technical stuff. And the way you calculate it in formula is that Rx is equal to Ix divided by the total cross-sectional area. That's how you calculate radius gyration. You take your moment of inertia with respect to the axis, take your total cross-sectional area, you take the square root, and that will give you the radius of gyration. Therefore, I take 141 times 10 to the 6 millimeters to the fourth. I take the total cross-sectional area, okay, the total, not just one. In other words, the top, the bottom, and the middle piece. And I do this, I end up, and of course, I should be ending up with millimeters because this cancels this, gives me millimeters squared. When I take the square root of millimeter squared, it gives me millimeters. So the right units for radius gyrations are millimeters because it's a distance with respect to where everything rotates. And that's why it has to be in millimeters. So that's with respect to the x-axis. Now, what we need to do is, of course, do it with respect to the y-axis, and therefore transforming this effect with the y-axis. Well, we have the same ratio. That doesn't change anything. The only thing is that now we transform all the dimensions parallel to the y-axis and not the x-axis. And therefore, we change the 300 to 30 millimeters. And of course, what's going to happen, this is what it's going to look like. So in other words, now it looks like we made a pancake out of our section because the concrete shrank parallel to the y-axis. In other words, I took the 300, I brought it down to 30, and now I calculate the properties based on this as if it's all steel with respect to the y-axis. Because if you remember, the y-axis was here. This was 300 millimeters this way, and therefore multiplied by 0.1. The concrete now shrinks down to 30, but the width stays the same, 200. So that's with respect to the y-axis. Now, I do the same thing. Now I call this IY because everything's calculated with respect to the y-axis, okay? And of course, I do the same thing, 1/12 the base times the height. Now, what you have to remember here is that even though this looks like 3 sections, I can actually treat this as if it was one rectangle. Does that make sense? I can treat this as if it's one rectangle. I have 30 here, I have 10 there, and I have 10 there. So this is the equivalent to a rectangle that measures 50 millimeters this way and 200 millimeters this way. So I treat this as if it's one rectangle, even though it might look like it's just one rectangle, and therefore it's 1/12 the base. So which is the dimension that is parallel to the axis is the 50, that becomes the B. which is the dimension perpendicular to the axis, that's a 200, and that becomes 200 squared. Is there any AD squared? No, because they all coincide. All the centroid here coincides with the centroid of my section, therefore I don't have, and that's how easy it is to calculate the IY, because everything coincides here. I don't have an AD squared. And therefore, now I've calculated my IY, and it ends up being 33.3 times 10 to the 6. So that tells me that, I don't remember the IX. Now that I have my IY, of course, I can go calculate my section modulus. Okay, IY over C, and what is C? C is the distance from the neutral axis. C is the distance from the neutral axis to the outermost fiber of my section, and in this case, it's symmetric. This is C and that's C, therefore I only have one section modulus. So whether I want to calculate the stresses here or the stresses here, it's one and the same. So therefore I take 33.3 times 10 to the 6 divided by 100, which is the distance from there to there. And now the radius of gyration now is, of course, the area is the total cross-sectional area here divided by the, the moment of inertia of this cross-section with respect to the y-axis divided by the area here. So therefore I get 33.3 times 10 to the 6, 20 times 50 is 10,000, and therefore RY is 57.7. That means that if this column would ever fail, it's most likely going to, you guys might not appreciate this, but if this column, if this was, for example, if this was my column here like this, and I had the steel plates like this, and the concrete here like this, and the steel plates like this, okay? If this column was going to be loaded here, okay, and of course this is my x-axis and that's my y-axis, okay. If this column would ever collapse one day, it most likely going to be collapsing in this direction here. In other words, it would collapse in this direction here, away from the y, not the x. That's what this tells me, because that is the weaker of the two based on this radius of gyration. It's always the smallest radius of gyration that will govern how the column will collapse. And that's what's good about knowing what this value is. And I believe, if I'm not mistaken. Oh, that's it. So guys, I hope some of this was just a review. I'm going to put the recording on pause.